Welcome to today's lecture. In the last class, we have seen generation of FM signals. In today's lecture, we are going to see demodulation of FM signals. In the last class, in the generation methods, we have seen two methods. One is direct method, another one is using indirect method. In today's demodulation lecture, we are going to see three methods. One is phase discriminator, the second is frequency discriminator, and the third one is using phase lock loop. Again, in the phase lock loop, we have two subdivision. One is using a linear equivalent and another one is using a non-linear equivalent. Demodulation of FM signals. What is demodulation? Demodulation is the process of recovering our original message signal from the modulated signal. Recovering the message signal or M of t from the modulated signal. Our modulated signal is S of t. The methods which we are going to see are using frequency discriminator, Okay, it can also be called as slope detector because it is going to detect the slope variations in the modulated signal. The second type of demodulation we are going to see is phase discriminator. The another name for phase discriminator is Foster-Seeley method. Third one is using the phase lock loop. In short, we refer it as PLL. First, we are going to see frequency discriminator. The first topic is, before we are going to see how the frequency discriminator in our demodulation works, we'll see what is slope detector and what is the frequency or characteristics, input output characteristics of slope detector. The purpose of slope detector is it detects the frequency variation, instantaneous frequency variations and instantaneous frequency variation. It converts this instantaneous frequencies into instantaneous amplitude variation. That is, variation in frequency is converted into variation in terms of amplitude. We are achieving this with the help of slope detector. Why we have to go for the slope detector? We know that our incoming signal is S of t, which is having an input variation from Fc plus del f to Fc minus del f. That is, this Fc is the unmodulated carrier frequency. Either it may have deviation, maximum departure of instantaneous frequency of the modulated signal from the unmodulated carrier signal. Maybe it will go for Fc plus del f, Fc minus del f. Del f is the frequency deviation factor, we know that, which we have studied in the previous lecture. Therefore, our incoming signal is having only the frequency variation. So, with the help of slope detector, we are using the help of slope detector. What it will do? It will convert the incoming frequencies with respect to amplitude variation. Therefore, we will have a signal. This resultant signal, we take it as V of t, which have here we have a frequency variation, either high frequency or low frequency. Here with respect to F max and F minimum, we will have A max and A minimum. That is, A we are representing for the voltage. Therefore, our amplitude modulated, now we are getting the from the frequency modulated signal, we are getting the amplitude modulated signal. So, what is the usual rule for converting the amplitude modulated signal or recovering the message signal from the amplitude modulated signal? We can simply use the envelope detector. Therefore, it will detect only the slope or amplitude of the envelope of the. Here we are detecting the slope, here we are detecting the envelope. So, with the help of envelope detector, we are recovering our original message signal. Now, we are going to see the input output characteristics of the slope detector. See, this is our with respect to frequency. This is the resonant frequency for our slope detector. Assume our resonant frequency is at F0. F0 is the resonant frequency of a slope detector. So, what it will do, our incoming frequency is lying here. F minimum to F max. So this is our F minimum, this is our F max. Assume this is our F max maximum frequency and this is our minimum frequency. So this region is referred as, this particular region is referred as the linear region of slope detector. So corresponding to this variations, we are going to get the amplitude variations here. So with respect to the frequency variation, we are going to have amplitude variation, A max and here A minimum. So this is the detector output. This region is called the linear region. This is a center tuned frequency FC. So this is the principle of slope detector, how our slope detector works and how the frequency variations are converted into the amplitude variations. In terms of the circuit diagram, here we have seen the block diagram and the resonant characteristics of the slope detector. We'll see in terms of circuit, what are all the blocks involved in it. So the first block is slope detector. So this R, L and C will together act as a slope detector, and which is followed by envelope detector. So by using the nonlinear device, diode, and followed by the tank circuit. So this is R, this is CL. So this region is called the slope detector. This part of region is called the envelope detector. Our final output is M dash of T, recovered signal. Our input is S of T, as FM of T. So this is our tuned circuit or slope detector, and here this is our amplitude and envelope detector. This output here, the output is amplitude modulated wave, therefore SAM of T. We refer it as, since it has instantaneous frequencies converted into amplitude variation, here we are referring it as instantaneous amplitude modulated wave. So what is the characteristics of this particular slope detector? It is having a linear region only around the F0. So this is our F0, this is our linear region. The center frequency is referred as FC. So this is our frequency response of slope detector. We are going to pass on the frequency modulated wave. So here we will use this space for this diagram. So consider this as our frequency modulated wave. So this is our F and this is our SFM of T. So what will be the amplitude modulated wave corresponding to this frequency? Our amplitude modulated wave will be go on like this. So this is our amplitude modulated wave. So what is the purpose of envelope detector? It will detect only this envelope. So what is going to be our output here? So this is in the SFM of T, the output of SAM of T, and what this is going to be the output of this envelope alone is going to be the output of here. This envelope alone is going to be the output of envelope detector. This is our V0 of T, or we can refer it as M dash of T. This is our recovered signal. Here the limitations, what are all may be the limitations in slope detector, or what are all may be the limitations are, it corresponds to spurious amplitude variations, because our instantaneous frequency is converted directly by using the slope detector into amplitude variation. Therefore, distortions will be present. And the second, sensitivity. How sensitive are slope detector? So, in order to improve the sensitivity of the slope detector, we are going for, instead of single tuned, we are going for balanced discriminator. Here we are having two resonance circuit. Instead of a one single circuit, we are going for a balanced discriminator. Instead of using a single frequency discriminator, we are going for balanced discriminator with the two resonant frequencies. Can we draw that diagram for? So, in order to boost up the sensitivity of our slope detector, we are going for balanced discriminator. So, what will be the diagram is, the diagram will look like this. Here again we have R, L and C with the center tapped transform, R, L and C here. R, L and C. So, again this side will have an envelope detector, diode, RL, CL. Again, here again we will have diode, RL and CL. So, here the output will be M dash of T or V naught of T. So, this is by using the balance detector. So, here we are going to apply in R is FM of T. By using the double tuned circuit, the resonant characteristics will look like this. See, this is the output of upper tuned filter. So, the linear region will be like this. This is with respect to F. So, this is the output of resonant frequency curve for, this is for upper, this is for lower circuit. So, with the help of two upper and lower frequency discriminator, our resonant frequency curve, this is our resonant frequency curve. Our linear region will get expanded from F0 of 2 to F0 of 1. Instead of, we have in the previous circuit we have seen our resonant frequency is only at F0. Here we have F01 and F02. This is the total response of both the tank circuits, that is in the upper and lower tank circuit or upper and lower slope detector. This is the total response. This is for upper curve and this is for lower curve. This is the total response. Separation between F01 and F02, this FR or FR, F0. In some of the books we have referred it as FR, in some of the books we refer it as FR. Both represents the resonant frequency curve. And the second topic in the demodulation is phase discriminator. In the previous topic we have seen how our frequency is, instantaneous frequency is converted into amplitude, and with the help of envelope detector how we have recovered our message signal. In this phase discriminator we are using the Foster-Seeley method of discriminator to detect the recover the message signal. We will see the diagram step by step. Here again we will have a center tap transform. We have a diode D1 and here diode D2. This is a diode D1 and this is a diode D2. the circuit arrangement will be look like this: plus and minus C1 capacitor, plus and minus C2 capacitor, and this is our L1, this is L2. Therefore, again this is our R1 and this is our R2. Okay. So, if we apply our unmodulated carrier signal, that is our FC of t or C of t, unmodulated carrier signal, what will happen? Our signal will be like this form. Therefore, either plus and minus or minus and plus, plus minus or minus plus, are always our input voltages V1 and V2 of t will be and our antiphase. And so, if here we will have antiphase, means here the output voltage will always be 0. Therefore, this two half wave rectifier, this is an half wave rectifier and this is an half wave rectifier, fed to the center tap transformer. Therefore, when we feed an unmodulated carrier, since we have an arrangement of antiphase, V1 and V2 are antiphase with each other, therefore here the resultant output will be 0 voltage. Therefore, whenever we have a center frequency of or a frequency with FC value is equal to FC, the resultant value will be 0. V1 and V2 are equal magnitude, but V1 and V2 are equal magnitude but opposite in phase. So, this is our first diagram. Second, if we add two capacitors into this circuit, in the same circuit, if we add two capacitors, let us, if we add here one capacitor, refer it as C3, and yet another capacitor here, we refer it as C5. What C3 and C5 will do? C3 will act as an parallel resonance circuit. That is, it forms a tuned circuit with resonant frequency equal to FC. The C3 will form a tuned circuit with resonant frequency equal to FC, and what C5 will do? C5 will shift the phase of the input signal by 90 degree, that is, it will shift the phase of the input signal, whatever may be your input signal, it will shift the phase to 90 degree. Therefore, this purpose of C3 is it will act as a resonance circuit with the center frequency is equal to FC, and this C5 will shift the phase of the input signal to 90 degree. And what is the complete circuit diagram for first relay is, see here we have introduced one capacitor called C5, and here we have a center tap transformer, diode D1, this is our diode D1, this is our diode D2, this is a L1, this is L2, and this is our C5. We have yet another capacitor over, inductor over here, this is L3, plus and minus C1, plus and minus here again C2, this is our R1 resistance, this is our R2. We have added C3 here, so this is our C3, and we are going to have another one capacitor C4, which will act as a blocking capacitor, so it will fed here. This path, the C4 and the L3 will act together. What the purpose of C4 is to block the DC, that is, it can be referred as DC blocking capacitor. The purpose of C5 is to shift the phase by 90 degree. The purpose of C3 is to act as a parallel resonance circuit. And what L3 will do? The entire incoming signal will be dropped across L3. Therefore, it will make the C3 will block the DC capacitor, DC current, and then this L3 will block the entire incoming signal. Our incoming signal, assume it as SF. It's a modulated, frequency modulated signal. Therefore, it is fed to the diode D2 directly here. So, therefore, if it is plus and minus, here also plus and minus, what will happen? Here the phasor diagram will be in the VA of T. When we have an unmodulated carrier signal, we don't have any voltage here. When we apply an incoming signal, for example, modulated signal, what will be the VFM of T? Here VA or VB of T. What is the VA? Here this voltage is referred as VA, and here this voltage is referred as VB. Both are in phase, therefore it is referred as VA and VB. Which are which are anti-phase? V1 and V2 are anti-phase with each other, that is V1 of T and V2 of T. This is with respect to VFM, VA or VB. So, from this here we have VA, what if it is plus and minus, since it is a center fed transform, here also plus and minus, therefore VA and VB are in phase, but when it reach here, V1 and V2 are anti-phase, therefore V1 and V2 are having opposite in direction. Then here when we apply C4 and L3, what will be the resulting voltage? This is our V1, V2, therefore we will apply positive current to diode D1 and here also, therefore both diode D1 and D2 will start conducting depending upon our incoming frequency. Therefore, the resultant voltage across D1 and the resultant voltage across D2 is referred as VD1 and VD2. When it will start conducting? When it have a voltage, positive voltage, forward bias. Here also when it have a forward bias. Since it acts as a resonant tuned frequency, it will start conducting only when it have either greater than or less than FC. So, this is our voltage across D2 and this is our voltage across D1. This is the phasor diagram for this circuit. So, whenever we have now we are getting into two conditions. Our incoming frequency, either it may have our incoming FM signal plus del F, that is, sorry, FC plus del F will be there, or FC minus del F will be there. Either it will have increasing frequency or decreasing frequency, that is maximum departure will either increase or decrease with respect to the unmodulated carrier frequency. So, we will take first condition, our FM is greater than FC, that is modulated signal frequency FC plus del F. Assume our incoming signal is having a frequency of FC plus del F. In that case, what will happen? Here we will have a positive and here we will have a negative. Therefore, the diode D1 will conduct more comparative to the diode D2. This is our V1 and this is our V2. Diode D1 will be conducting more compared to that of D2. Therefore, this is our VD2, this is our VD1. What will be the resultant phasor vector? Here VD2 also will shift in this direction. No, we'll redraw this diagram again. When our input frequency changes, that is if FC plus del F is greater than FC, that is in this condition, that is FM is greater than FC. In this condition, what will be our phase? So, this is our resulting voltage. This is our VD2, this is our VD1. Large total voltage across D1 and reduced voltage across VD2. This is our V1, this is our V2. This is our VFM. Therefore, since we have large voltage across VD1, output will be positive. VD1 is greater than VD2. The second case will be when I have an FM, input signal frequency is less than FC, that is in the case of FC minus of del F. In this case, what will happen? It will shift the direction. This is our VFM, this is our V1 and this is our V2. Therefore, VD2 will be conducting more compared to that of VD1. So this is our VD1 and VD2. In this case, what will happen? VD2 will be conducting more with respect to VD1. And then what will be the output? Here output is positive, plus and minus, here minus and plus, therefore output will be negative. By comparing these two conditions, the difference in voltage is VD1 and VD2 is the demodulated output. That is the difference in voltage D1 and D2 will give the recovered message signal. This is our Foster-Seeley discriminator. This circuit is susceptible to noise, therefore Foster-Seeley network should be followed by a noise limiter circuit. Therefore, we are going to apply an SFM of T to the Foster-Seeley discriminator. It will detect the phase variations, and then the resultant will have the message signal, which should be followed by a noise limiter circuit. It will have some noise. Therefore, to eliminate our noise, we are suppressing by the help of limiter circuit. This is our recovered signal. Next is phase locked loop. The third subdivision in demodulation is phase locked loop.